Hi everyone. This talk is about an efficient post-quantum PKE from RLWR with simple security proof. I am Parhat Abla. In this talk, I will talk about the backgrounds on hard learning problems and public key encryptions from RLWR and RLWR and its security proofs. And then I will talk our constructions and its security proof. After all, I will show the performance of our scheme. A public key encryption scheme consists of three algorithms: public key keygen algorithm, encryption algorithm, and decryption algorithm. The keygen algorithm on inputs security parameter outputs two keys, public key and secret key. The encryption algorithm inputs public key and its message M. It outputs the ciphertext. After receiving the ciphertext, the decryption algorithm uses its secret key and decrypt the ciphertext to a corresponding message M. Right now we have many encryption schemes, RSA, LGAML, and other encryption schemes which are based on the integer factor problems or discrete log problems. And their schemes are secure because of these problems. IFP or DLP are hard to solve classically, but in the quantum world, these problems can be solved very efficiently by the Shor's algorithm. So the quantum computer is near the future, and fortunately we have a quantum-resistant candidates: code-based, hash-based signatures, multivariate-based signatures, lattice-based cryptography, and isogeny-based exchange. Among them, the lattice-based schemes are simple and efficient. They are linear and highly parallelizable, and secure under the worst-case hardest assumptions, and can construct many functional encryptions, like fully homomorphic encryption, and so on. But public key encryption schemes based on the lattice problems, which are very inefficient, and so in 2005, Regu introduced the learning with errors problem, but later on the ring version of ring learning with errors problem are introduced. Let's make some notations. The R is notation for the ZX over the X to the N plus 1, where N is the power of 2, and RQ is R over the Q times R. In the ring RLWR problem, there's the search and the decision version of two types of problems. The search version gives many RLWR samples like AI and BIs, polynomial many AI BIs, and asks to find S, where BI is computed as AI times the secret S plus an error EI. The decision version asks to distinguish AI and BI from the uniform over RQ and RQ. For the hardness, we have a reduction from the decision ring RLWR problem to the worst case SIVP on either lattice problems. That means the worst case SIVP problem on either lattice is hard, that the ring RLWR problem is hard. Let's recap the ring RLWR problem. This is similar to the ring RLWR problem, but we don't have to sample a Gaussian distribution or error distribution here. The search version of ring RLWR problem gives many polynomial many AIs, many AI and BIs, where BI is computed as AI times S and rounded to P. Round to P, which means multiply this entity to the Q over P and take the nearest integer. The decision version asks to distinguish AI and BI from RQ times RP. For the hardness, we have a reductions from ring RLWR to ring RLWR. When the number of samples are unbounded, polynomial unbounded, we need the modulus Q be a super polynomial. For the bounded samples, we also have a similar reduction, but the polynomial modulus is enough. Fortunately, bounded samples are sufficient for many crypto systems, and including the PKE. So we just need a polynomial modulus in the crypto system. Let's recap some encryption schemes based on RLWR and RLWR. In the RLWR problem, on the left, which is very simple, the PK is a RLWR sample here, and the SK is S, the secret of the RLWR. And in the encryption procedure, there was two ciphertexts, C1, C2. C1 is very similar to the RLWR sample, and C2 is very also the RLWR sample, but B is from a previous RLWR sample. In the decryption procedure, we just compute C1 minus C2 minus C1 times the secret S and run to the 2. RLWR problem, we don't need these error distributions here. We just run them, and the PK is a RLWR sample, RLWR sample. In the encryption procedure, we don't need this error. We just introduce this deterministic error by rounding them, and the C2 is similar to them, and decryption is similar. We observe that the public keys, secret key or ciphertext, and other operations in the RLWR-based PKEs are in RQ, but in the RLWR, they related to many other rings, like RP, RT. That is the difference. So the security proof also have some difference. So let's recall the IND-CPA security for a public key encryption. IND-CPA is a fundamental security we can require from a PKE, which is also called semantic security or positive security. And this security is defined by the game like this. The challenger firstly computes a public and secret key by KJ algorithm and sends the PK to the adversary. Adversary then maybe create many ciphertext oracles, and then outputs two equal length message M1 star and M2 star. And the challenger encrypts one of the message, challenge ciphertext, challenge message, and generates challenge ciphertext C star, and send it to the adversary. Adversary will guess which message is encrypted and outputs the final guess. And if adversary's guess is right, so we call the adversary wins the game, and the advantage is defined like this. Now we recall some security proofs from RLWR and RLWR based schemes. RLWR based in PKEs, security proof is very simple. We just we use hybrid games. Game 1 in game 0 is the original game, just describable, and game 1 is simple, different from game 0. We just replace B from here, and it's uniformly sampled from RQ instead of sampling it as a RLWR sample in the original game. And ciphertext is indifferent. And in game 2, we just replace challenge ciphertext with a random messages, a random element from RQ. So the C2 is now independent of the message mu. So adversary's advantage in the game 2 is 0, and game 2 to game 1 is indistinguishable from the RLWR problem, and game 1 to game 0 is also indistinguishable from RLWR problem. So adversary's advantage on the original game is negligible or very close to 0. In the RLWR problem, it was somewhat complex. In the game 1, we just replace B by RP, which is from the RLWR assumption. instead of straightly go to the game 2, we introduce some games, intermediate games, game 2 prime here, where B is sampled from RQ. Maybe we need another game to exchange the C2 and analyze some exchanges are not affects security. So this is subtle, complex, and different from the RLWR problem. RLWR problem, each game hope uses one RLWR assumption, and RLWR problem, they require T. The T is used here, and by running, and the P times over Q. It was smaller than this one, and T divides P, P divides Q, and which results in many public key encryption schemes need these parameters are power of 2, in which the T divides P and the P divides Q. In our paper, we construct a encryption scheme based on RLWR. We overcome the complex security proof by introducing an intermediate problem, or just introducing some errors here. Our construction is like this. In the Kgen, it's similar to the RLWR problem. B is generated from rounding and Q to P. And the encryption, instead of sampling a R here, which is also sampled from RLWR-based encryptions, we also sample a uniform element from minus Q over 2 times P to Q over 2 times P, which is different from the previous schemes. And this is uniform error. And then we compute C1 as a RLWR samples, A times R, and round to the P. And our second ciphertext C2 is computed by Q over P times B. Now B is belongs to the RP because we round to the P, and plus a U. And then we multiply by R and compute some mod Q and round to the P, and then add our encoding of the message. And the decryption algorithm is very similar to the previous schemes. For security proof, we also use hybrid games. In game 1 is our original game, and in game 1, we also replace B with a random element from RP. In game 2, game 2 is indifferent from game 1 because we just replace B with RP and replace this one with a B. This is identical, and we prove it in our paper. So this is not a new game. This is also is a game 1, and last game we just I replaced the challenge ciphertext with the uniform elements in RP. So now the C2 is independent with our message, and the adversary with the advantage is close to 0. So our proof is very simple, and it's very like the RLWR problem, RLWR-based PKEs, but with very simple security. So we didn't need a additional error distributions when we encrypt, but we have many advantages over RLWR-based PKEs. For parameters, we give 2 set of parameters, scheme 1 and scheme 2. Our scheme 1 reaches 128-bit security, and our scheme 2 reaches 256-bit security. Our space complexity is present here. Our scheme in the 128-bit secure scheme, we have a smaller public keys and secret keys, but our ciphertext is much larger. In 256-bit security scheme. Our scheme performs not good that NIST's other schemes, but also it's acceptable. We also implement our scheme and other NIST PQC standardization finalist schemes in our MacBook Pro equipped with i5 CPU with 3.9 GHz. Here's our scheme 1 in the Cajun algorithm. We are very fast. This is because our parameters are very small here, and encryption and decryption algorithms are also comparable with the finalist of the NIST PQC standardization. And 256-bit security scheme, also comparable with the other schemes in the NIST post-quantum standardization competition. And so our scheme is also performs very well, and its security proof is very simple as RLWR based encryption schemes, but it's very like RLWR based schemes.